right. Welcome, everybody, to the Saktigo Identity First Security Summit 2022. And the talk that you're about to listen to is on quantum safe cryptography. And you can believe me when I say that we're going to be doing sort of a 101 version of this topic. Some of the discussion points, even just the bullet points within this webinar, are going to be so deep that they could take up entire webinars onto themselves. We're going to try to pack as much information as we possibly can into a fairly short period of time. Before we start, I will introduce myself very quickly. My name is Jason Sirocco. I'm the CTO for PKI at Saktigo. Been around this business of PKI for quite a long time. But part of what I find interesting about my background and the opportunities that I were given throughout my career is that I did have a number of years of offensive malware research time. And that gave me a unique perspective within cybersecurity and in PKI in general. And I think that what that was able to give me is a special perspective, not just from the defender point of view, which is something that I think a lot of us who work at Saktigo have been working with, but I also have the perspective of thinking about what's it like from the other side. In other words, thinking about how to build our products and how to build security products, keeping in mind the special mindset that the offenders actually have. And it's a different mindset completely. And I think that it's important to mention that with respect to this topic of quantum computing and especially quantum safe cryptography, because what we are talking about is the future threat of quantum computers against the current cryptographic algorithms that we use in PKI. So in terms of today's discussion, we're going to have a brief discussion in terms of understanding quantum computing and quantum cryptography, two very large subjects that we could spend a lot of time on. We're also going to talk about what the actual threat is and what the threat specifically is to PKI and the timing, because obviously the threat isn't here today, but it is the reason why we're speaking about this topic right now at length is because of the fact that within our careers, and in fact, within a certain number of years, probably less than 10, we will be facing a time when the current cryptographic algorithms might be deemed deprecated because of quantum computing. So how are the vendors in the PKI space responding to this? I'm going to give some of the Saktigo perspective. And I think, the call to arms to everybody watching this webinar is it's time to get your hands dirty in terms of understanding the new cryptographic algorithms and what you're going to have to understand and do in order to bridge the current technologies to the future technologies. So, quantum. You hear that word quite a lot, and we're going to spend a few moments on this slide talking about a few important topics here, but really this comes down to ones and zeros. Literally. The classic bit, if you've ever been into computer science, you've ever heard even just the analogy that everything with computers is ones and zeros, that's absolutely true for the classic computers that you guys run today. Your mobile devices, your laptop, stuff you do in the cloud, watching a Netflix video, right? Everything is ones and zeros. The thing about quantum that's interesting is quantum introduces something different to the ones and zeros. It introduces what's known as a superposition. Therefore, not only is there a 1 and a 0, just like a light bulb being turned on and off, there's also a superposition. What is that? Well, we could probably have entire conferences on what that is, the superposition. But suffice to say that it's basically a form of physics that is applied to some sort of an object, whether it's an electron, a photon, right? We could get into this very, very deeply, but just keep in mind that from a data standpoint, from an information standpoint, what we are talking about is something either being a 1, a 0, or this something else that's recorded. So it's no longer a bit, it's what's known as a qubit, a quantum bit. And that quantum bit is able to encapsulate the 1 or the 0 or the superposition, right? This incredibly interesting mix that's so different and so much more information rich than the classical bit of 1 and 0. All right. That's a lot of terminology that probably isn't explained terribly well. You might have to go and watch about 20 YouTube videos even to just start to begin to understand this. But what's important about this to cryptography? And I would say it's this. Classical computers right now utilize factorization. Goodness, more math, right? I can't promise there won't be any math in this webinar, but really what this means is this. Classical computers are very good at a lot of things, but one of the things they're not good at in terms of speed is factorization, an algebraic term, which basically means that for the RSA cryptographic algorithm, as an example, one of the reasons why it's such a good way of creating a secret is because a computer, a classical computer, has to go through all the steps. There's no shortcuts in going through all the steps to find large prime numbers. Classical computers are slow at determining large prime numbers. It just happens to be one of the truths about classical computers. You might have also heard about the ECC algorithm, or the elliptic curve cryptographic algorithm. It doesn't use prime numbers per se, but it's using the principles of a specific defined mathematical curve. And in order to find points on that curve, once again, there's a factorization that's required. And that factorization, again, is very difficult for a classical computer that's only using 1s and 0s in order to be able to do the math and determine the locations of those points on a curve. And that's why we have very safe cryptographic algorithms that we use today. You've heard about, it would take a computer X number of millions of years to be able to solve for a specific cryptographic algorithm, and that's the truth. But when we're talking about quantum computing, this richness of information that's brought about by not just having a 1 and 0, but also a superposition, when you employ special other forms of algorithms, right, very specifically the Shor's algorithm, and I'll spell that out to you, it's S-H-O-R. You can look that up. If you apply a quantum computer with Shor's algorithm, that can use that superposition, that extra richness of data, to be able to more quickly break down the factorization that's necessary for the RSA algorithm as well as the ECC algorithm. So to make it sort of a little bit more simplistic, what it means is that as quantum computers gain more stable qubits, we're going to enter a situation where software can be written for those quantum computers, those very stable, large qubit numbered quantum computers are going to be able to potentially threaten the current cryptographic algorithms that are used in cryptography, right? We're talking about RSA and the ECC algorithm very specifically. So I think it's very important to distinguish a couple of topics that you might be stumbling across in technical journalism. This webinar is mostly about the cryptography part of it, the actual algorithms, ECC and RSA, but you might also come across basically the idea of quantum key distribution. It's actually a different topic that we're not going to cover as much here today. Believe it or not, whenever you're encoding information on that superposition part of a qubit, there's an incredibly interesting aspect to that part of a qubit, which is if you're actually encoding a superposition against one qubit, it could actually be entangled with another qubit. Isn't that crazy? It's actually a bit spooky, but in fact, It's been proven in science. And so therefore, the ability to have 2 qubits, probably in reality more than that, but technically in theory, at least 2 qubits that have their superposition spun. This is an interesting term. You can actually then separate those 2 qubits from each other and be able to then have identical information encoded in 2 different places. So imagine being able to have a secret that can be exchanged between 2 places by merely taking advantage of the physical property of entanglement of qubits. Okay, I think we got to move on because this stuff starts to get absolutely crazy. Let's go back down now to what NIST has told us, right? The big standards body down in the government of the United States. Very smart people have been brought together in order to help us to try and solve these problems. And their comment, well, let's read it here because it's actually quite important. If large-scale quantum computers are ever built, they will be able to break many of the public key crypto systems currently in use. Isn't that interesting language, using the word if and ever built? In other words, they're not saying it's inevitable. They're not saying it's guaranteed. I found this language to be quite interesting. However, I think that it is important enough to note that I think as an industry and the science community together has needed to actually bring all the brains necessary to try to become quantum resistant. In other words, moving beyond the RSA and ECC algorithms in order to be able to get to the next stage, in order to be able to get to a quantum resistant algorithm. So let's move on with the statement. This would seriously compromise the confidentiality and integrity of digital communications on the internet and elsewhere. So let's make that real world. I like to take these complicated statements and break them down and make them real for you. And what that means is when you're browsing to a website and you're using HTTPS, right? You're using an SSL certificate off of that web server. It means that chances are the RSA or the ECC cryptographic algorithms are being used to encrypt the communication between yourself and the browser. Well, what happens if that encrypted stream is being recorded right now? It means that in the future, that stream potentially could be decrypted by using a large quantum computer, a sufficiently large quantum computer, as well as Shor's algorithm and some specialized software could potentially decrypt that recorded stream even from today. It could even affect digitally signed documents potentially. So this should make things interesting to you. It's not just about encrypted streams of information or signed documents in the future. It's about current information that's being encrypted with those algorithms. Maybe today they cannot be decrypted, and that's good. But at the point of the quantum apocalypse, when quantum computers are able to decrypt even today's information, which has been recorded by, let's just call it the bad guy, could also be decrypted in the future. That's an important consideration that I think is not said in this NIST statement, but it's something that you need to keep in mind. And that's why you need to start getting your hands dirty in this today. Start learning. That term quantum apocalypse that I just mentioned, it's to capture your attention. It's not a term that I've coined, but it certainly is an important one that I think does need to capture your attention. And I think we've mentioned a lot of this already in terms of what the concern really is. But let's keep in mind that the current RSA and ECC algorithms are sound. That's important to keep in mind. What it will take, what the quantum apocalypse is kind of defined by, is going to be this convergence of technologies, of quantum computers, right? And so if you've taken a look at any of the technical journalism on this, Microsoft, Google, other large megatech companies that are involved in building quantum computers. Some of them have taken the route of using very, very cold computers in order to stabilize those qubits. Some other approaches have been to build these computers in a very large manner that can actually work at room temperature. Some of them actually use a different kind of quantum computer known as quantum annealing, which is something completely different. And there's other vendors in that space. And one of the things that you'll notice is that they're leapfrogging each other in terms of the number of stable qubits through time. And so even though today there's not a sufficient number of stable qubits within these quantum computers to achieve the quantum apocalypse, what things that you need to keep in mind are that eventually they will. This linear step forward motion of more and more stable qubits is something that you're going to see through time. And people much smarter than me on the topic have basically said the chance of there being sort of a big eureka moment where a whole new class of quantum computers might come out that jumps across a whole chasm of stable qubits into something much more powerful, that is probably not as achievable as this slow progression of achieving more and more slowly through time. And this is what gives us a little bit of confidence in saying when we think the quantum apocalypse may occur. That's an important point. So let's ask that question to ourselves. When will the quantum apocalypse happen? And this isn't me saying it. This is taken from some very, very smart people, mathematicians at the university level. And some of them have said that there is a probability that we could be looking at sufficiently powerful quantum computers by around 2026. Well, we're recording this session around 2022, and I can tell you we're not that far away. So therefore, that's why you'll see a lot of effort being made in order to be able to achieve quantum resistant algorithms for cryptography and being able to get ready with the technologies to bridge you to the new cryptographic algorithms. So what I'm going to invite you to do is to get your hands dirty, get involved with your CA, and basically let's propose solutions and start planning now. So when you're preparing for the quantum apocalypse, what does that mean? When I say get your hands dirty, what does that mean? Well, what I can tell you, so Saktigo has actually developed a portion of the company. We've actually carved out some resources, and we like to call it Saktigo Quantum Labs. And first of all, I got to tell you where to go for that. At the bottom of this slide, you'll see saktigo.com/quantum-labs. I invite everybody who was interested in watching this webinar to go to that landing page, that website. And what that'll show you is that this partnership with ISARA has yielded some very interesting toolkits that we can use together. And what those toolkits will allow you to do is to actually start issuing, through a certificate authority, the ability to issue certificates that are quantum resistant, but at the same time compatible with hybrid systems. Isn't that amazing? What an incredible bridge technology. Now, I believe in this virtual summit, there will be other talks by some other vendors about even other approaches that you'll be able to start thinking about. But I think when you're dealing with a certificate authority right now, I think that you've got to start looking at what I think is the number one resource for quantum resistant PKI right now. And not just talking about it or reading a white paper about it, but actually starting to using software that will allow you to issue certificates, what we're calling hybrid certificates, that will allow you to bridge the previous cryptographic algorithms to the ones that you will be using in the future. So let's talk about those hybrid certificates for a moment. So right now, if we typically are dealing with discrete types of certificates. Right now, obviously, you can be dealing with traditional digital certificates that use ECC or RSA. You can issue those all day long right now without any extra work. Or you could go off and issue yourself a quantum safe digital certificate through other means. The problem is that that quantum safe digital certificate will not work at all with the traditional systems. What I find very interesting, and this is such a smart idea, is if you take a look at the protocol of a digital certificate in today's world, the X509 standard, if you use a clever feature, which is to add a field to that digital certificate, what you're able to do is essentially create a hybrid certificate. And that hybrid digital certificate is able to encapsulate the traditional digital certificate with the traditional algorithms, essentially exposed on the outside, and then have the quantum certificate actually on the inside of it. So in other words, ultimately your secret, the thing that you're encrypting, can be kept within the innermost portion of the certificate, the quantum protected, the quantum resistant portion of the certificate. However, have the outer part of the certificate exposed traditionally so that traditional systems can actually handle it. Very clever. And so if you think about it, traditional certificates are more like just your traditional Fort Knox, where you have the big, you have the big building and the vault. And that's great within the current world. That's fantastic. The problem is that after the quantum apocalypse, that the number combination to that vault might be able to be cracked. So what we need to move to is actually something a lot closer to a medieval castle and keep. In other words, you have the outer walls of a castle that are going to be analogous to your traditional digital certificate with the traditional cryptographic algorithms, ECC and RSA. And then the keep, the inner portion of the castle, is an entirely other fortified portion of the digital secret, which would then be encrypted with a quantum resistant algorithm. What this achieves is the best of both worlds. This allows you to have an interoperable certificate exposed on the outside, whereas on the inside, you're protected from the problems that are going to be associated with the quantum apocalypse. What a great idea. So why would you partner with Saktigo for quantum safe cryptography? Well, we've got a lot of expertise in running certificate authorities. It's our business. It's what we've done for multi-decades. And we do have expertise in quantum cryptography. We are partnered with the best in the business. I think that the biggest thing you need to keep in mind is that this is all about uptime. It's about being reliable. It's about having high security standards. It's about being able to protect that CA. It's about being able to protect the private keys. It's about being able to have the software necessary to be able to do all these things and keep yourself protected and bridge yourself from today's world to the world beyond the quantum apocalypse. That's why you want to partner with Saktigo. Now, let me finish this off by basically saying that if you liked this talk, I have a colleague named Tim Callan, and he and I actually speak on a podcast that's called Root Causes. And you can go to just about any of your favorite podcast sources. Quite often I go to SoundCloud and re-listen to some of the podcasts when I need to remind myself about something. And I invite you all to be able to go and have a look at that. So everyone, just as a reminder, my name was Jason Sirocco, and I'm the CTO for PKI at Saktigo. And what you've been watching is a webinar on quantum safe cryptography. This was part of the Saktigo Identity First Security Summit of 2022. Thank you very much for watching.